My voice is clear? Okay, so hello everyone.
Yes, sir.
Hello everyone, good evening to all. My name is Abhishek Pandey. I am a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. So today we are going to talk about week 9 assignment. Okay, so it is basically on the singularities and Lorentz expansion. So before going to start, I want to give one announcement that tomorrow you guys having one live session na given by Nitin. Hello.
Yes, sir.
Yeah, so he will take that live session at 11 a.m. Okay, tomorrow at the same link. Okay.
In the morning?
Yeah, in the morning 11 a.m. Okay.
Okay, sir. Okay.
So I have written in the comment box. Okay. So let us start now. So this is just the basic of singularities. So I will just recall these things. So let Z0 belongs to C is said to be singularity of F. So if F is not analytic at Z equals to 0, Z0, but every neighborhood of Z0 contains at least one point at which F is analytic. Okay. And singularity is of two types, isolated and non-isolated. Like as the name suggests, so isolated singularity is defined like this. If there exists a deleted neighborhood of Z0 such that F is analytic in that neighborhood, okay, so that point will be called isolated singularity. And non-isolated singularity means for every neighborhood of Z0 there exists a point except Z0 at which F is not analytic. Okay, so these are the examples. You can go through this. So I will just quickly recall the Lorentz series development. So let F be an analytic in this annulus. Okay. Then Fz can be written like this, where this convergence is absolute and uniform over this, over closure of this. Okay. So here R1 and R2 is what? So R1 is greater than is capital R1 and small r2 is less than capital R2. Okay. And the coefficients is given by this formula. Okay. So this is the integral over the curve gamma, where gamma is any circle this. So you have this annulus. Okay. So gamma, you have this annulus. So basically gamma is any circle in between. Okay. So basically this integral doesn't depend upon this gamma. You can take any circle. Okay. In the annulus. So this is the important theorem, just keep this in mind. So classification of isolated singularity using Lorentz expansion. So let Z be an isolated singularity of F and let Fz equals to this be its Lorentz expansion in this annulus. Okay. Then, so Z equals to A is the removable singularity if and only if An equals to 0 for all negative integers. Okay. And Z equals to A is pole of order M if and only if this M, A minus M, is non-zero and An equals to 0 for all n less than equals to minus M plus 1. Okay. So basically it can have only finite number of 1 by Z terms. Okay, in Lorentz series expansion. If Z equals to A is a pole, so this term can have only finite number of 1 upon Z minus A powers. Okay, this can only be finite. Okay, finite number of times. Z equals to A is isolated. Here I should write essential. Not isolated. It should be essential singularity. So Z equals to A is an essential singularity if and only if. So this term An is not equals to 0 for infinitely many negative integers. Okay, if this is the case, then Z equals to A is an essential singularity. So now let us start the questions. solution. So, first. Okay, so let us look at this first question. So omega I will be any open connected subset of C. Okay, means it is a domain. Okay. And all curves are assumed to be rectifiable. Okay. So now let us look at this one. So basically first thing is fz is equals to sine z by z. Okay. So at 0 it is not defined right now. Okay. So can you tell me the expansion of sine z? Can anyone tell me?
Z minus Z cube by 3 factorial plus
Yeah.
Z
So z minus z cube by 3 factorial plus z 5 upon 5 factorial and so on. Okay. So this will be basically 1 minus z square upon 3 factorial plus z 4 upon 5 factorial and so on. Okay. So as you can see that if you let z tends to 0, so f of 0 will be 1. Okay. So and this is basically the Lorentz series expansion of f around 0. Okay. So by this theorem, this all the negative terms are 0 in this one. Okay. So it is clear that so clear to everyone? So this first option is true. Okay. So this is clear to everyone? Hello?
Yes, sir.
Yeah. So now let us look at the second. So basically this is also true. So this is asking z sine 1 by z has an essential singularity at z equals to 0. Okay. So fz is equals to z sine 1 by z. Okay. So once you expand this, so you will get z into 1 by z minus 1 by 3 factorial z cube plus 1 by 5 factorial z5. Okay. So this will be equals to 1 minus 1 upon 3 factorial z square plus 1 upon 5 factorial z4 and so on fz. Okay. So in this Lorentz series expansion, these negative terms, okay, these are infinitely many, isn't it? Negative power of z. Hello, is it clear?
Yes, sir.
Yeah. So what will be 0? What kind of singularity?
Essential.
Yeah. So z equals to 0 is an essential singularity. Now let us look at the third option. The third option is basically false. What does it says? So this is true, this is false. So it is saying, let me write it here only. So, okay. So it is asking sine square 1 by z plus cos square 1 by z has an essential singularity as z equals to 0. So basically sine square 1 by z plus cos square 1 by z is equals to 1 for every z non-zero. This is true? Is this fine to everyone?
Yes, sir.
Yeah. So at 0, what kind of singularity it has? So once you take the limit z tends to 0, what it will be? as z goes to 0, where does this goes? This goes to, so basically this is a constant function, okay? Basically this is 1 for all z non-zero, okay? So at 0 what we can define? So now define gz is equals to 1 and 1. So z is not equals to 0 and z equals to 0. So z equals to 0 is removable singularity, na? So this is fz. So this. Is it clear? Hello? Please respond, anyone?
Yes, sir. Clear, sir.
Okay. So let's look at the fourth option. So fourth option is saying suppose f and z are holomorphic functions which have removable singularity at the point z naught. Then this fz by gz has a removable singularity at z naught. Okay, so let us look at this one. So this is false. We will construct an example. So basically let fz is equals to z square by sin z. Okay, and but this we cannot take because so sin z will be 0 at some points. Okay, so, basically what we can do is that so sin z is 0 at when? So sin n pi is equals to 0, isn't it?
Yes, sir.
Yeah. So n equals to 1, it will be pi. Okay. So basically sin z does not have any 0 in the unit disk except z equals to 0, isn't it? Hello? And you take gz is equals to zpq by sin z. Okay. So now fz by gz will be what? This will be 1 by z. Okay. Which has a pole at 0. Okay. So this is also not true. Or you can also take like this, I mean, this example you can also so you can take it like f. So you can take it like fz is equals to sin z upon z, okay, and gz is equals to sin z upon what can we take? Hello? Or you can basically you take like so, just take z, okay. So basically it is holomorphic and at 0 is a removable singularity. So z belongs to d minus 0. Okay. and you take zz equals to z square, okay, and you do fz by zz equals to 1 by z, so pole. Okay, now let us look at the fifth question. So fifth question is, suppose f and g are meromorphic functions. So meromorphic function means, and so its only singularity is pole. Okay, so suppose that f and g are meromorphic functions such that f and g have poles of order 3 at point z naught, then the function has a removable singularity at point z naught. Okay, so both f and g have poles of order 3 at z naught. What does it mean? So if fz has a pole of order 3 at z naught, means we can write minus 3 gz, okay, where g is holomorphic and g of z naught is non-zero. Okay. Also, so basically if g of z naught is non-zero, there exists a neighborhood where it is non-zero. Okay. Also, gz, this, let us write capital Fz, okay, where this I can write it as, this I will write it f, okay, and gz we can also write like this, gz, where g is holomorphic and g dash z naught is non-zero. Oh, sorry, g of z naught. Okay, so now once you do fz by zz, what you will get? Fz by gz. Okay, so it has a removable singularity. It has a clear?
सर कैसे बोल सकते हैं by g?
This we need to calculate na, fz by gz.
Yes.
Yeah.
So capital F by z, but how can we say that it is a removable singularity at z?
So basically this gz is what? This gz is non-zero at z naught, okay, and holomorphic. Fz is non-zero at z naught and fz is also holomorphic. Okay, so fz by zz is also holomorphic.
Yes, sir.
Clear?
Yes.
So basically it is g of z naught is non-zero, means there exists a neighborhood. See, f of z naught is non-zero, so f z is non-zero for some ball centered at z naught comma r1, okay, and gz is also non-zero for some ball centered at r2. You just take the minimum of r1 and r2. Okay, so now fz by gz is holomorphic in this ball and gz is non-zero in holomorphic scenes. So clear?
Yes, sir.
Okay. So let us look at the second question. So actually some misprinting is there in this question. So this should be fz is equals to summation n equals to m to infinity an z to the power. Okay. So now recall the previous case. So solution. Okay, so first one. So basically f such that punctured unit is, okay, so d minus 0 to c is meromorphic. Meromorphic with Laurent series expansion as summation n equals to m to infinity n z to the power n, okay, for an integer m such that am is non-zero. Okay, so let us look at the first option. First option is basically true. So it is saying that if m is less than 0, then the function f has a pole of order minus m at z equals to 0. Clear? So let m is less than 0. Okay, so fz is basically, so if m is less than 0, minus m is positive. So n equals to m to infinity an z to the power n is basically an z to the power m plus a naught plus a1z plus and so on a minus m z to the power minus m and so on. Okay, so what you do, you just take z to the power m common. Okay, so this will be am a naught z to the power minus m plus a1 z to the power 1 minus m plus and so on a minus m. Okay, what will be this one? Minus 2m. Okay, now let us look at this term. Okay, so call this term as g. So z to the power m into gz. So so what is g of 0? Am, and it is non-zero. Also g is holomorphic. Thus fz can be written like this. Okay, so f has a pole of order minus m at z equals to 0. This is clear? Any doubt in this one? Do you have any doubt? See, all these things.
Pole of order minus m.
Yeah. Since m is negative, na. So suppose m is minus 3. So this will be z to the power minus 3. So what will be the order of the pole? Minus of minus 3 means 3.
Yes, sir.
Yes, sir.
Yeah. Okay, so let us look at the second option. This is also true. So second option is the function f has a removed singularity at z equals to 0 if m is greater than equals to 0. So this is also true. So if m is greater than equals to 0, basically fz is summation n equals to 0 to infinity a n z to the power. So this is holomorphic only. Okay, so this is trivially true. Let us look at the third option. This is also true. What does it says? So the function f has a 0 of order m at z equals to 0. So 0 of order m, what does it mean? Zero of order m means mth derivative at that point is non-zero and non-zero and fn0 is equals to 0 for all n is less than m. So this is the meaning of 0 of order m, isn't it? Okay.
Yes, sir.
Yeah. So third option is, so fz is equals to summation n equals to m to infinity a n z to the power n. Okay, and here m is positive. Okay, m is positive. So basically an is equals to 0 for all n greater than equals to 0 and m. Okay, what does it mean? This means that fn0 is equals to 0 for all n greater than equals to 0 and less than m. Thus f, and observe that fm0 is what? fm0 is am. This is non-zero. Okay, thus f has a 0 of order m at 0. Clear? Is this clear to everyone? Let us look at the fourth question. So this is false. What does it says? So if f has a pole of order m positive at z equals to 0, then fk has a pole of order m to the power k, okay, at z equals to 0. So fk is basically f into f, okay. So basically, so let fz is equals to 1 by z, okay, so that f has a pole of order 1, okay, at 0. So what will be fz into fz? This is what? 1 by z square, okay. So so this has a pole of order 2, okay, at 0, okay, but 2 is not equals to 1 square, okay. So this is false. So basically it is saying that this has a pole of order m to the power k, okay. Now let us look at the last option. So this is, if this is the case, then m equals to 3, okay. So this is easy to do, just write this. That question is true. Let fz is equals to sine z upon z to the power 4. So this is basically 1 upon z to the power 4, z minus z cube upon factorial 3 plus z4 upon, oh sorry, z5, no? Factorial 5 and so on. Okay, so this will be what? 1 upon z cube minus 1 upon under the vector z plus z upon factorial 5 and so on. Okay, so once you compare with this one, this thing, what you get? M equals to, so actually in the question I am writing this one, okay, like this. So what is your M? So M should be minus 3, isn't it?
Yes, sir.
Yeah. So basically this is a misprint in this question, okay. So that's why you don't consider this, or you consider this one, okay. So M is minus 3, okay. Now let us look at the third question. So third question I will prove in general. So just pay attention on this one. Okay. So let us prove a theorem. Let Z naught be an isolated singularity of F, then Z naught cannot be pole of Gz is equals to e to the power f. Okay. Okay. So Z naught is an isolated singularity of F. Okay. So first case is let if Z naught is removable. Okay. So in this case, what does it mean? Limit Z tends to Z naught, Fz exists. Okay. So limit Z tends to Z naught, Gz will also exist, isn't it? Okay. Thus G has okay. Now second one is if Z naught is pole. Okay. So if Z naught is pole, then 1 by F has removable singularity isn't it? Basically you define 1 by Fz in some neighborhood of okay for some delta positive, and here if Z equals to Z naught. Okay. Okay. So since h of 0 is equals to h of Z naught equals to 0. Okay. So h of Z naught is 0. So by open mapping theorem, what we are getting? H of this thing Z minus Z naught is less than delta. This image of this will contain some ball centered at origin, isn't it? This line is clear to everyone? Just let me know. If you have any doubt, you can ask. This is clear?
Yes, sir.
Okay, nice. So therefore the range of F over, so this is H. Okay, now we are talking about the range of F. Just keep in mind that this H is nothing but 1 by F. Okay, over Z minus Z naught, this contains a neighborhood around infinity, that is there exist R greater than 0 such that mod Z is greater than R is contained in F of this line is clear? Just let me know. This is clear?
Yes, sir.
Okay. So if the range of f over this contains this one, what does it mean? It also contains the set two pi. Okay, clear? Okay. Now exponential of s means image of s under exponential mapping. This is nothing but c minus 0. This will cover the whole complex plane except 0. So e to the power fz is also c minus 0. Okay, for every z minus z naught greater than 0 and less than delta. Okay, thus z naught must be an isolated singularity, essential singularity. So basically every sufficiently neighborhood of z naught, every sufficiently deleted neighborhood of z naught, basically the image of this under e to the power fz is c minus 0. So it has to be essential singularity only. Okay, clear?
Yes, sir.
Yeah. So e to the power 1 by z cannot be a pole at z equals to 0. Basically, this is what? This has essential singularity. Essential singularity at 0. Okay. Now the next is now the next question, just look at this one. Okay. So the set e to the power 1 by z for all z belongs to punctured unit disk is dense in C. Okay. Since z equals to 0 is essential singularity, so in every neighborhood, the image of that deleted neighborhood is dense in C. This is nothing but Kazhslow Weierstrass theorem. So this is true. Now the image of the function, this function, the image of the function 1 by z such that unit disk minus 0 to C is dense in C. Is it? Is it the case? Like the image of this is dense? So basically what is this? Mod z is less than 1. So 1 by mod z is greater than 1. Okay? So it cannot be dense. Isn't it?
Yes, sir.
Yeah. So this is also wrong. Now suppose f is function holomorphic on the unit disk, then image of f is dense. Okay, so this is also not true. You just take fz is equals to z. This is holomorphic mapping and its image is unit disk itself, which is not dense in C. Okay, so this is also not correct. Okay, so third is done. Let us look at the fourth question. Okay. So basically it is f such that omega to C such that f is meromorphic with at least one pole. Okay. So the sum of two meromorphic functions in this set is always meromorphic in this. So this is not correct. So first option is false. What you do, you take, let this is equals to d. Okay. Fz is equals to 1 by z. Gz is equals to minus 1 by z. So f plus g of z is basically 0. This doesn't belongs to this. Whereas f belongs to this, comma g also belongs to this. So this is not true. The product of two meromorphic function in this one is always meromorphic function in this one. Okay. So what you do, you take, this is also false. So what you do, you take fz is equals to z minus 1 by 2 into z, okay, and gz is equals to z upon z minus 1 by 2. So both f comma g belongs to this set, but f into g of z is basically 1, okay, which doesn't belongs to this set. Clear? Now the next question is, the quotient of two meromorphic function in this is always a meromorphic function in this. So the quotient, so this is also false. Okay, so what you do, you just take f and g, this one. So the quotient will be minus 1, okay, but minus 1 doesn't belongs to this one. Okay, so this is also false. The product of meromorphic function in this one and a holomorphic function is always a meromorphic function. Okay, so what you do, you take fourth one, na? So let us take fourth one. Fourth one is also false. Okay, so you take fz is equals to 1 by z and gz is equals to z. So f into g of z is basically 1, but 1 doesn't belongs to this one. Here f belongs to this one and g is holomorphic. Okay, now let us look at the fifth option. So fifth option is none of the above. So this is true. Fifth option is true. This question is clear to everyone? Hello?
Yes, sir.
Yeah. Okay, fine. So let us look at the fifth question. So given that f of z is equals to 1 upon 1 minus z on basically d minus 0, this is nothing but, okay, so we have to check what is the Lorentz series expansion. So basically f is analytic in this set, this annulus, okay. So f has a Lorentz series expansion what is it? Summation n equals to minus infinity to infinity a n z to the power n, okay. And what is your a n? So this is nothing but 1 upon 2 pi I integral over gamma fz upon z to the power n plus 1 dz, okay, where gamma is any circle, okay, mod z equals to r is clear. So now let us calculate what will be this one, okay. So now observe that, so this is nothing but en is equals to 1 upon 2 pi I integral over gamma. What is your fz? 1 upon 1 minus z into z to the power n plus 1 dz. So now if n is positive, n is greater than equals to 0, what will be your an? So this is nothing but fn 0 upon n factorial, isn't it? Just observe this one, and this will be 1 only. Just observe this one.
Yes, sir.
Okay, fine. And if n is less than 0, what is your an? So an will be 1 upon 2 pi I integral over gamma dz upon 1 minus z to the power n plus 1. Okay, so now observe that once n is less than equals to 0, this term will go upward. Okay, means suppose n is minus 1, this will be 0. Sorry, this will be 1. Suppose n is minus 2, this z to the power n plus 1 will be z to the power minus 1. So this will be z upon 1 minus z dz, and this function is holomorphic in unit disk. Okay, so for each n, this is nothing but 0 by Cauchy's theorem. Whether this is clear to everyone or not?
Yes, sir. Clear, sir.
Yeah. So Lorentz series becomes fz is equals to summation n equals to 0 to infinity z to the power. Okay, so this is the Lorentz series. So now let us look at the options. The Lorentz series expansion of the function this has non-zero with negative indices. Is it true?
So negative indices means
Yeah, negative indices means a negative power of z. This basically these are the coefficients, and what will be negative indices? N is less than 0. So it is saying an is not equals to 0 for n is less than 0. Is it the case? What we have proved?
equal to 0 for n less than 0.
Yeah. So this is false. Okay. The Lorentz series expansion of this coincides with the power series. So this is true. This we have proved. Now we are changing the annulus. Now we are taking this annulus. So let us work in this one. Okay. So now consider the annulus. What is it? Z belongs to C such that mod Z is greater than 1. Okay. So basically F is analytic, and I'll take in this one. So F has a Lorentz series expansion. Okay. So summation n minus infinity to infinity an z to the power n. Okay, where an is nothing but 1 upon 2 pi I integral over gamma fz upon z to the power n plus 1 dz. So where gamma is mod z equals to r and r is greater than 1. So any r greater than 1 will do the job. So what we will do, we will check what is A naught. Okay. So let us check what is A naught. So A naught is nothing but 1 upon 2 pi I integral over gamma. So you take gamma, let r equals to 2. Okay. So this gamma let mod z is equals to 2. Okay, your fz is 1 upon 1 minus z, and this will be z dz. So this can be written as 1 upon 2 pi I integral over dz upon integral over dz upon 1 minus z plus integral over gamma this. Okay, so once you calculate this one, you will get a not equals to 1, which is non-zero. Okay, so now let us look at the option. Okay, so according to this question, according to this option, has the Lorentz series expansion this one? Okay, means for n equals to 0, what is the coefficient? This expansion is there. What does it mean? For n equals to 0, what is your an?
0.
Yeah, 0. But what we are getting? A naught is? Yeah, which is non-zero. Okay, so this is not true. And the Lorentz series of the function this is unique irrespective of the annulus center at 0. But this is not the case. Basically, in this annulus center at 0, what is your A naught? Hello? Okay, so A naught is 1, but if you want to check, let us check it for n equals to minus 1.
सर ये ऊपर वाला सही है, ये जो है ना सिग्मा n इक्वल टू -1 to -infinity minus z raised to n.
Yeah, this is true. Why?
नहीं, थर्ड ऑप्शन ये.
So you are saying it, this is correct.
हाँ, यस.
Why?
1/1 minus z है, अगर उसकी सीरीज लिखते हैं ना, if I take minus z common
Huh?
and then write the series.
Yeah, so no, so that is basically 1 plus z square. This you are saying, na?
Yes, in denominator we take minus z common. So 1 minus 1 upon z and take it on numerator and then write down series.
Basically what you are saying. So you are saying 1 upon 1 minus z. Now what to do?
1 upon minus z common निकालते हैं. 1 upon minus z.
So 1 upon 1 minus z. You want to take z common out?
Minus z common out.
Yeah, minus z. Then 1 minus 1 upon z. Then
Okay. Then 1 minus 1 upon z, take it on numerator and write down series.
so basically just remember that 1 upon 1 minus x is equals to 1 plus x square. This is valid when?
Yes. Mod x less than 1.
Yeah, mod x less than 1. Okay.
So here mod z is greater than 1 means 1 upon z less than 1 होगा ना?
Where it is written that mod z is greater than 1. Okay, yeah. So mod z is greater than 1. So now you can do minus 1 upon z into 1, then 1 plus 1 by z. This you are saying, na?
Plus, yes.
1 plus 1 by z plus 1 by z square, yes, and so on. Okay, so this will be basically what? Minus 1 by z minus 1 by z square minus 1 by z cube and so on. Okay.
Yes. So n varies from -1 to -infinity 1, sir.
Okay, just wait. I think so this would be 0, this integral.
A not 0.
So this integral is what? Can anyone calculate it? then I think this integral will be 0. I think so, I don't know. But once you calculate the coefficients of this one, I think this integral will be 0 then. Yeah. Yeah, so basically this is correct. Okay. Let me check here. Yeah, this idea is correct. You just take out the minus z common, okay, and okay, so this idea is correct basically. So you will get this expansion, okay. Hello, Darsana? Yeah, so you will get this expansion, but this is here all the coefficients are -1,
Yes.
and here
Okay, z is to n. Yes,
yeah,
yes.
so this is not correct. I think
Yes, sir.
this integral I have made some mistake calculating. This will be 0, I guess. Anyhow, so this is the way of I mean, this is one way you can check. You can basically directly calculate all this integral, okay. Anyhow, the Lorentz, so this is clear, na? This is not correct. Basically these all coefficients are
Yes, sir.
-1 and here it is +1, okay. Yeah. So the Lorentz series of the function this is unique irrespective of the annulus centered at z equals to 0, okay. So now once you see that in this annulus, okay, Lorentz series expansion is this, and in this annulus Lorentz series expansion is this. So both are different, okay. So these are not unique. Is it clear?
Yes, sir.
Yeah. Now let us look at the last question. So the first question, okay, basically let us look at this one first, other questions. So it is given that P is a non-constant polynomial, then this function, okay, you just look at this function, Pn upon z to the power n, basically n belongs to the integer, okay. So can anyone tell me what kind of singularity it can have at z equals to 0? So Pn is not equals to 0 for infinitely many what? Hello? This is clear? Hello? Anyone? Darsana, Prakash?
No, sir.
So
Pn is not equal to 0.
for infinitely many negative n, P is a polynomial, na? So it can have only finitely many zeros.
Okay. Yes, sir.
This is clear, na?
Yes.
Yeah. So you will always get infinitely many negative powers of z, isn't it?
Yes, sir.
So z equals to 0 is an?
Pole.
No, pole you cannot get, na, infinitely many negative. pole only finitely.
Essential singularity.
Yeah. So this will be essential singularity. So this is not correct and this is not correct. Now let us look at the first question. So f says that C to C is holomorphic and non-constant. Okay, so it is saying the image of f is dense in C. Let us suppose, if possible, let f of C is not dense in C. Okay, that is, what does it mean? There exists a ball centered at some point R and radius R such that FC intersection with this ball is phi, isn't it?
Yes, sir.
Yeah. So basically what does it mean? This means that mod of fz minus z naught is always greater than R for all z belongs to C, isn't it? Now define G such that C to C by Gz is equals to 1 upon fz minus z naught. Okay, so G is entire. Okay, and modulus of Gz is what? Modulus of Gz is hello, please anyone tell me.
Okay, sorry.
Hello,
Sir,
yeah,
less than
please.
Less than R. Less than R.
Less than 1 by R.
Yes, 1 by R.
Yeah.
yeah.
So less than equals to 1 by R. So what does it mean? Entire function bounded.
Yes.
So G has to be,
Removable singularity.
yeah, so G has to be constant, which is a contradiction. Okay, so FC is always dense in C. Okay, so that's all. So this one is clear now? Yeah, now if anyone have any doubt, please ask me. Feel free to ask.
Sir, fz equal to z square minus 5z plus 6.
Fz is equals to Z square,
Z square minus 5z plus 6
okay,
upon z by z minus 2.
okay.
So, is it removable or पोल ऑफ ऑर्डर 2? बिकॉज इसके फैक्टर भी होते हैं ना, न्यूमरेटर में आप देखो तो इसके फैक्टर्स होते हैं z minus 2 and z minus 3.
Yeah, so it is Z minus 2 and Z minus 3. So Z minus
Yes.
2 get cancel out. It will be Z
Yes.
minus 3. So it is a removable singularity.
Yes, but if we do not factorize, तो पोल भी हो सकता है ना?
नहीं पोल नहीं हो सकता है क्योंकि anyhow if you put Z equals to 2 here, so this is also 0, this is also 0.
Yes.
So as limit Z tends to 2, what you will get?
0 by 0.
Yeah, 0 by 0 form. So once, so then you apply what we call,
Hospital's rule.
yeah, L'Hopital rule. So L'Hopital rule you apply, you just differentiate upper part and lower part, you will get -1.
Okay.
Yeah, clear?
Yes, clear.
Anything else?
Sir, function with 0 of order m, तो उसका मीनिंग क्या होता है?
Okay, so basically function f has 0 of order m at 0 at z naught means mth derivative at z naught is non-zero, and you take any derivative at z naught, this will be 0 for n less than m naught. Clear?
Yes, sir.
Yeah. So basically 0th derivative at z naught means f of z naught only. So this is the 0 of order m. Anything else? Any doubt? Prakash, Thangesaran, Rajesh?
No, sir.
Okay.
Thank you, sir.
So if there is no doubt,
One minute,
yeah.
one minute, sir. सर अगर हम हमें f के बारे में पता है तो can we say anything about 1 by f?
Yeah. So like मतलब हमें f के बारे में क्या इंफॉर्मेशन पता है, लाइक उसके सिंगुलरिटीज?
हाँ यस, इसकी सिंगुलरिटीज पता है कि सपोज f इज रिमूवेबल सिंगुलरिटी, तो 1 अपॉन f के बारे में हम लोग कैसे बोल सकते हैं, मींस कौन सा लॉजिक अप्लाई कर सकते हैं?
Okay, so see, limit z tends to z naught, अगर f z naught पे रिमूवेबल सिंगुलरिटी है तो 1 by f भी z naught पे रिमूवेबल सिंगुलरिटी होगा ना, बिकॉज लिमिट z tends to z naught f exist. Okay, so 1 by f also exist, isn't
बट
it?
ये लिमिट 0 भी हो
But
सकती है ना सर?
yeah, that's what I'm coming. So if it is 0, okay, then 1 by f has a pole at that point. Are you?
Okay, sir.
Yeah. Is it clear to you?
Yes, sir.
And suppose f has 0 at some point, 1 by f has pole at that point. And if f has pole at some point, then 1 by f has removable singularity at that point. Clear? Dasana, is it clear?
Sir, f has 0, so 1 by f has pole.
Yeah, so f of z is equals to 0 at some point, then 1 upon f z at 0 you can, this is basically infinity
Yes, yes, sir. Yes.
as a limit. Okay.
Okay. Clear, sir.
Anything else?
So non-isolated essential singularity, can you tell me something about it?
Yeah, so basically that is a way of defining. Some authors may say non-essential singularities, but see, isolated singularities had 3 types: pole, removable and essential. Okay, non-isolated means at that point z naught, okay, for every neighborhood of z naught there exists a point where f is not analytic. Okay, like if you take this one, fz is equals to log z. Okay, so the principal branch of logarithmic is analytic on this one, basically this negative real axis. Okay, so you take the z equals to 0. Okay, so basically you just cut it out, this negative real axis. So log is analytic c minus this one. Okay, now you take z equals to 0. So you take any neighborhood, okay, this contains the point where f is analytic and also contains the point where f is not analytic. Okay, so these kind of singularities are non-isolated. Okay, and sometimes we also call it as non-isolated essential singularities, like sine 1 upon sine 1 by z. You can call it as non-isolated, non-essential singularities. Basically, non-isolated essential singularities. Basically, essential singularity means in every neighborhood of that point, the image is dense in C. If such kind of criteria is happening for some function, that singularity is called isolated singularity. But always remember that we put isolated singularity in essential singularity in this part under this umbrella. Okay, isolated singularity. So isolated singularities have three parts: removable, pole, and essential. Does it clear your doubt?
Yes, sir.
Thank you.
Yeah. So some authors define like this: non-isolated essential singularities. Okay.
Thank you, sir.
Okay. Yeah. Thank you.
Thank you, sir.
Yeah, thank you, everyone.
Thank you, sir.
So I will just close the meeting.